Good evening from Bangkok. Welcome to the Lines webinar organized by AIGS. I'm Michelle, glad to see you again. So we are very happy to hear that many people are going back to work. So that means the regular schedules are back. It is a very exciting news. And I have another good news to share with you that we will continue with this webinar for a few months because we got so many good comments from our attendees that they said this webinar have been very useful for them. So we are very happy to hear that, and we will try our best to connect more people and more professors and speakers to share their knowledge with us. So tonight we have a very important guest speaker, Dr. Claudio Milisenda, and he is a CEO of DSEF, German Gem Lab in Idar-Oberstein. He has been working there for more than 25 years. So this is marvelous. And he is a delegate of the Tourmaline to IGC and CIPJO, where he currently served as the Vice President of Gemological Commission. And he got his PhD in Earth Science. So he's a very frequent speaker, and he has published many articles in mineralogy and gemology and geochemistry. And he's also the member of the Laboratory Manual Harmonization Committee. So he has very good background. So we are very honored to invite him tonight to be here to give us a talk about the treasures of the Tourmaline Group. So I hope you will enjoy it. So now I will give the stage to Dr. Milisenda. So hello, Dr. Milisenda, are you there? Let me try to invite you to start your video. Okay, so can I hear you?
I can hear you.
Yes, now I'm inviting you to turn on your video.
Yes, hello everybody. Sawadee to Thailand, and welcome to everybody around the world, wherever you are. I hope that everybody is in a good mood and healthy. So I'm sitting here in my office in Idar-Oberstein, which is actually the very heart of the European colored stone industry. And we're looking back at a tradition of gemstone mining and cutting and trading that dates back more than 500 years ago. And today I'm talking about a gemstone, which is as important as is the ruby for Thailand. This is the tourmaline for the people here in Idar-Oberstein. Now, let me just switch on my presentation so that I can share it with you. I hope that everybody can hear me well.
So I still cannot see your presentation. Is some problems?
Yes, just a second.
Yeah, okay. So yeah, okay. Now we're done. Thank you.
Let me just go into the presentation mode. So I'm talking about the tourmaline. As I mentioned, a very important gemstone because it has so many colors. Tourmaline can virtually occur in every color. And it were actually the people from Idar who added tourmaline to the list of coveted gemstones. Now, and that was about 150 years ago. If you are looking back to the history of tourmaline, it was used actually long before that as a gemstone in times when people didn't know actually what tourmaline is. Now, what you can see here, this is the so-called Saint Wenceslaus crown that was manufactured in 1346, which forms part of the Czech crown jewels. In the front here, you can see 1, 2, 3, 4, 5, 6 red stones and a blue stone. Now, this crown has been examined in detail only in the late 1990s by my friend Jaroslav Hirsel. And what he shows here is the crown illuminated with ultraviolet light. And what you can see here is that 5 of the 6 red stones show a strong red luminescence. And he identified these stones as spinel, whereas the center stone, which does not show luminescence, is actually a rubellite tourmaline, so a red tourmaline. And it was thought to be a ruby. Now, it was only in 1700, at around 1700, when in the Netherlands, and the Dutch were probably the first who brought tourmaline from Sri Lanka to Europe, they gave the name Tourmaline, which was derived, or which is derived from the Sinhalese term Touramali, which stands for multicolored stones. Now, again, tourmaline is a name for a whole family of minerals. And these minerals have in common a crystal structure that can be described by a general chemical formula. Now, what you can see here, these are typical crystal habits of tourmaline. You commonly have these trigonal prisms, very often with striations on these prism faces. Then in the top view, you can see the pyramidal faces. Commonly, you have 6 pyramidal faces. And here on the right, you can see how well reality matches theory. So these are trigonal crystals. And what is also important for tourmaline is that these crystals are polar. I come to that in a minute. When you apply pressure to tourmaline, for example, by rubbing, or if you apply heat and subsequent cool it, they develop an electrical charge. So a positive charge on one end and a negative charge on the other end of the crystal. And the old Dutch used this to clean their smoking pipes, their meerschaum pipes. So they heated up a tourmaline and then they pulled out ashes of the pipe. And this is why they call these crystals of tourmaline also Aschentrecker, which means ash puller. And this effect is called piezo and pyroelectricity. So piezo by pressure and pyro by heat. Now, if you look at the next slide, you can see a very nice tourmaline crystal. This one is from Namibia. And since it is a trigonal crystal, the vertical crystallographic CX is also the optical X. And here on the left and on the right, you see the crystal structure of tourmaline, here parallel to the CX and here perpendicular to the CX. I'm not going to describe this in detail, but I want to point out that tourmaline commonly consists of SiO4 rings, which are these yellow triangles, actually tetrahedrons, which form a hexagonal ring here. And then they are intercalated with a distorted BO3 groups. And these rings and planes and columns actually are linked by various cited cations and anions. Now on the right, here it is important for me to point out that all these tetrahedrons point in the same direction. So they are polar. So for those who are familiar with crystallography, very commonly you use these elements of symmetry to describe a crystal or or a crystal system. So, and one of these elements of symmetry is the so-called mirror plane. So there is no mirror plane perpendicular to the optic X, and that makes the crystal polar, and this is the predominant reason or cause for the pyro and piezoelectricity. Now this crystal structure, which all the tourmalines have in common, can be explained by a general chemical formula, which is listed here. XY3Z6T6O18BO3VW. Now, and these are just positions in the crystal lattice, which I just showed you on the slide before. And then various cations and anions can be incorporated into these various positions. And you see that, for example, at the X side, there can be sodium, calcium, potassium, or it can be even vacant. And most of the coloring elements, like, for example, chromium, vanadium, but also manganese and iron, are predominantly incorporated in the Y and in the Z position. And because the chemistry is so complicated and so many elements can be incorporated into the crystal structure of tourmaline minerals, they can produce all these sorts of colors that you can see here. So tourmaline can occur in every single color, in all sorts of mixtures of colors, and very commonly in one single tourmaline you can see even 2, 3 or more colors. And depending on which element is in these various positions, then we can subdivide the tourmaline group into various tourmaline minerals. And this list just shows those tourmalines which occur or which have some importance in gemology. The most important one is Elbaite tourmaline, named after Elba Island in Italy. Then there is lidicotite, named after the former president of the Gemological Institute of America. Dravite, chromium vanadium dravite, named after the river Trau in Austria. Ubite, named after the Uba province in Sri Lanka. Thylacite, the manganese-rich tourmaline, named after the village of Thylaicina in Madagascar. Shirl, which is commonly the black tourmaline, which is named after the village Chorlau in Germany. Burgerite, after M.J. Berger, a crystallographer from the US, and Rossmanite, the famous George Rossman researcher at Caltech in the US. So these are the minerals, or the minerals that can occur in gem quality of the tourmaline family. But you hardly hear these names in the trade. Commonly, we hear the various color variety terms. And whenever people talk about tourmaline, the color green springs to their mind. And among the first tourmalines that appeared on the market were the green tourmalines from deposits in Brazil. There are famous mines like, for example, Cruzeiro mine, the Todo Mundo mine, and many more that produced these sort of tourmalines, which were more sort of a bottle green, like it's can see here, but also some very nice bright green specimens like this pair here. And this type of quality is known in the trade as Brazilian tourmaline. So bottle green to yellowish green and yellow green. So this was the first type of variety that appeared actually in the market in larger quantities, particularly from Brazil. Now, if you look at the tourmaline, here you can see a very nice crystal from Afghanistan. And you look at the tourmaline using a two-field polarizer to observe the pleochroism, you can see, or you will see, that the pleochroism in tourmaline is very distinct. As you can see here, this is actually the line that divides the two polarizing fields. And you can see here, in this case, a lighter color and a darker color. This is very distinct in tourmaline, and because of that, and because of the fact that tourmaline in a certain direction of the crystal I'll show you that, can produce actually single polarized light. Tourmaline actually was used very early as a type of polariscope. So from two tourmaline prisms cut parallel to the optic axis, mounted here a piece of cork, which is then again mounted in rotatable brass discs, you were able to separate optically isotropic from optically anisotropic stones. And for this, tourmaline crystals were used. And coming or making a few comments on the identification of tourmaline, I just mentioned the pleochroism, which is quite important. When you look at the green tourmaline and like this rectangular faceted stone here, and you put it on the refractometer, and I hope that still people are using refractometers, and you measure it, and if the table is located or oriented exactly parallel to the optic axis or the crystallographic C-axis, you get a single value. We actually measure the direction of single refraction. So then when you rotate the stone, you get the birefringence, and if you rotate the stone so that the table is perpendicular to the optic axis, you get maximum birefringence. Now, in green tourmalines, the pleochroism is very extreme, so that if you look in the direction into the optic axis, the stone actually is almost black. So in green tourmalines are commonly cut so that the table is parallel to the optic axis. And so you have here commonly in green tourmalines elongated shapes, whereas in red tourmalines, the color that you see perpendicular to the optic axis is too light. So the most attractive color is the color that you see when you look into the optic axis. And for this reason, in red tourmalines or pink tourmalines to red tourmalines commonly are cut in more rounded shapes. Now, if you put this stone with the table down onto the refractometer, you always get maximum birefringence because you always measure the refractive index or the refractive indices parallel to the optic axis. So the perpendicular to the optic axis, sorry. So the cutter has to know this so that you can actually orient the rough stone in the correct way. Now let's have a look at an absorption spectrum of a tourmaline, of a green tourmaline. In this type, in this case, a tourmaline which is sort of a little bluish green, which you, for example, typically find in Namibia. This is a very beautiful bluish green tourmaline. And the two spectra that you see here are polarized. So one is the spectrum for the ordinary ray, and this is the red spectrum, and the blue one is the one for the extraordinary ray. And we look here at the absorption, and this is a spectrum that shows actually the absorption spectrum between 250 and 1500 nanometers, so from the ultraviolet until the infrared. Now we're actually only interested now in the visible light range, roughly between 300 and 700 nanometers. And here you see the corresponding plot of these spectra in the CLab color circle. Now, when we look at the red spectrum, we see first of all a prominent absorption band of iron located at around 720 nanometer, so which actually absorbs the red part of the spectrum. And we see here another small band at around 400, with maximum at around 420, which is due to iron titanium charge transfer. And this causes an absorption minimum or transmission maximum in the green part of the spectrum. Now, this band is not there in the extraordinary ray. So the extraordinary ray produces a bluish green color. So in total, this stone is bluish green, basically colored by iron and titanium charge transfer, and towards the ultraviolet light, there's also an additional manganese titanium charge transfer. Now, stones from Namibia were first found just shortly before World War I. And they have been discovered in Usakos in the Erongo region in western Namibia, where they are located in Pan-African pegmatites, or in stones that have been formed during the Pan-African orogeny. I'll come to that later. But here you see a draw that I made a couple of years ago, I think it's almost 20 years ago, to show the location of various gemstone deposits in relationship with the geology. And you can clearly see that in Africa, there are these Pan-African orogenic stones here, rocks here, and along that you commonly find occurrences of pegmatitic derived gemstones, including tourmaline and also aquamarine. And what you also find in these Pan-African orogenic belts, the famous Mozambique belt here, is corundum. Now, Namibia is located approximately here. So the tourmalines I'm talking about now are from this area, but we will later on see also stones from the other areas. Now, these stones actually appeared on the market, or were actually exported from Namibia to Hamburg in Germany in 1910, 1911, and then came to Idar a few years later. At the very beginning, nobody wanted to have them, but then people were very much interested in stones once they appeared in a little larger quantities on the market. Now, these stones actually have a bluish tinge, as I mentioned already, and this bluish green in the trade is known as African tourmaline. So for the green stones, we have the Brazilian tourmaline, and for the bluish green stones, the African tourmaline. So two types of various qualities of tourmaline. And so this does not mean that when you hear the trade African tourmaline, that the stone comes from Africa, or Brazilian tourmaline, that the stone comes from Brazil. It refers to color. Brazilian tourmaline, more this bottle green, yellowish green. African tourmaline, more the bright green with bluish hues. Now, already in 1932, it was George Will, the founder of the German Gemological Association, found out that when you heat treat these bluish tourmalines, you can get rid of the blue, producing a green. And at these times, actually, green was more sought after than blue. And so all of these tourmalines have been treated to remove the blue component. And this can be done at temperatures at around 650 degrees centigrade in about 1 hour. So we did this in our own oven here in our laboratory. And is there a possibility to identify that? Now, commonly tourmalines, those which are in the trade, when they are of good quality, are pretty clean. So unlike in corundum, there are not that much inclusions available from which you might conclude that the stones is heat treated. Well, very often you cannot tell. In green tourmalines, sometimes if you put them on the refractometer, you can see these multiple refractive indices, as you can see here. And this is actually due to the fact that during the heat treatment, there will be produced some so-called vicinal phases, very small, submicroscopically small phases, which actually produce these multiple readings. So if you see tourmaline with these multiple readings, you can be pretty sure that the stone is heat treated. Now later, other areas in Namibia produced bluish-green tourmalines. One farm which is quite well known, actually two farms which are quite well known, is the Neuschwaben farm in the Caribbean area in the Erongo region, which was first discovered in 1923 and which still is producing some stones today. And then also the Ochua farm, also located in the same area in the Erongo region in Namibia. They are producing very, very nice stones. We had the opportunity to visit this during the International Gemological Congress in 2017. And so this is the photo I made there. We see some very nice bluish-green tourmalines, and these are some cut stones which are from that mine. So you can see a nice bright blue, even greenish blue. You can see green stones, you can see greenish blue stones. But these are typical Namibian tourmalines. And in Namibia, you also find stones which are blue, greenish blue, or indeed pure blue, as you can see in these stones here. And here is a corresponding absorption spectrum, again polarized, and you can actually see here that manganese titanium or iron titanium band is lacking, leaving behind the transmission maximum here in the blue area, and this is why the stone is blue. And you can see here the points, the corresponding points here in the color circle, which plots in the blue area. And these blue tourmalines actually are known under the name indicolite. Now, one may ask why this is maybe derived from the indigo blue. Why is it not written with the G? It is actually derived not from indigo, it is derived from the term indicum, which is a Latin term for a plant. Another green tourmaline, which is also very attractive, is a green tourmaline that is not colored by iron, but one which is colored by chromium, but more generally by vanadium, a combination of vanadium and chromium, a stone which first appeared in the trade in the late 1950s and originates from Kenya and the border between Kenya and Tanzania. And this is collectively known in the trade as chrome tourmaline. Although in most cases, the tourmaline is predominantly colored by vanadium. Now this stone, from a mineralogical point of view, is a mixture, or as we say, a solid solution between the tourmaline minerals dravite and uvite. And occasionally, this stone shows the so-called Usambara effect, which is actually not, strictly speaking, a color change, as we can see this in alexandrite, which is due to different type of illumination. Here you can see different colors, predominantly green and also red, depending on the path length of the light that travels through the stone. So this effect is known as the Usambara effect, a change from green to red, depending on the path length of the light traveling through the stone. Now we come to the red tourmaline. The red tourmaline, here you can see a very nice specimen from Afghanistan, and this is a suite of red tourmalines with the larger stone here weighing about 20 carats, and these stones are colored by manganese. Now, there is a difference in the trade between a red tourmaline and a red tourmaline that is called rubellite. Now, in the trade, those tourmalines are called red tourmalines, which change their color to sort of a brownish orange hue in incandescent light. Whereas rubellite is only referred to those tourmalines which retain their nice red or pink color in both daylight and in incandescent light. And we commonly find these stones in Brazil, in Nigeria, in Afghanistan, and in the United States, for example, the Pala district in California. Note that many red tourmalines are irradiated. Normally, they are pink before irradiation. Actually, they are pale pink, and then the stones are heat treated, then they become colorless, and then they are irradiated, and this irradiation actually oxidizes manganese, and then the stone became bright pink. However, also the natural pink tourmaline is colored by manganese and by manganese 3 plus, which is actually a result of natural ionizing radiation. So unfortunately, we cannot distinguish between artificial irradiated and natural irradiated red or pink tourmaline. If we look at the absorption spectra of red tourmalines, now with red I will include red, pink, purple, violet. And when we are looking at manganese-rich albite tourmalines, most of these red ones are actually albites. There are two types actually. One, as you can see here, with absorption centered at around 530 due to manganese 3 plus, leaving behind actually transmission areas in the blue-violet and in the red, and the mixture of this will result in purple color. Here on the right, there is a different spectrum in a way that manganese produces more than only just this one band. It produces several bands, as you can see here. So in addition to the 520 band, there is another one here at around 700. There is another one here at around, let's say, 580. You can see here a transmission minimum also in the red and also one here in the blue-violet. But the resulting color strongly depends actually on the exact position of the transmission minima and minimum and maximum, and also on the location, the absorption coefficients here. The difference actually between the two spectra here is indeed that these stones tend to show an orange or brownish hue when they're illuminated with incandescent light. So this is the rubellite and this is then the red tourmaline. In 1983, it was Schmetzer and Bank who were working at our institute here in Idar, who first described this type of tourmalines, which were derived from a locality near Lundazi, which is in eastern Zambia, very close to the border to Malawi. And at that time, they described these stones as manganese-rich tourmalines. They also were discovered in pegmatites or recovered from pegmatites. And there were not that much stones available in the trade until about in 2000, when people heat treated the stone, and from this type of stones, from this type of tourmalines, which were sort of brownish, they produced this bright yellow, Canary type yellow tourmaline, and which then became very famous under the name Canary tourmaline. And there is commercial production since 2000, but we have our institute described it already in 1983. Canary tourmaline, very attractive, actually sort of neon green tourmaline. And what is so special about this tourmaline? Well, you can see here, first of all, the absorption spectrum and the points in the color circle. Absorption is due to manganese 2 plus, and there is also then increasing absorption towards the ultraviolet light, which is a result of manganese, titanium, intervalence charge transfer. And if you look at the chemical composition, you can see that Canary tourmaline is enriched in manganese. So 7.02 weight percent, which is quite high for an albiite. So it's actually an albiite silicate solid solution. So that is the most characteristic feature or property of Canary tourmaline, the high manganese concentration. Whenever you talk about tourmaline, you also have to mention these, or we also have to mention these tourmaline crosscuts. Now, we looked already at the trigonal symmetry of tourmaline, and here you can very nicely see the color zoning following actually the trigonal symmetry of the stone. You can see here that these stones include actually many colors in a single stone, very typical for tourmaline. These stones that you can see here, the red core with the green rim, is also known as the watermelon tourmaline. Basically, these are albiite tourmalines, whereas this type of tourmalines, which commonly come from Madagascar, are chemically leucotype tourmalines. Very attractive stones. So that was the situation of tourmaline until about 1987, when all of a sudden these type of stones appeared on the market. Colors which have never seen before in tourmaline, colors which have never seen before in any other transparent gemstone, colors which then were referred to as neon, electric, swimming pool blue. And these stones actually come from a certain locality in Brazil, particularly in the state of Paraiba. Now, this is the famous tourmaline hill, Morro Alto. Morro Alto just means high hill, with the famous Mina da Batalha, the Batalha mine, where these stones have been first discovered. And Batalha produced for a period of about 5 years, approximately 5 years, very nice stones. But then already in about 1991, 1992, these stones were mixed with stones that came from another mine called Boquerón, or which more known under the term Mulungu, which is located not in Paraiba, but in the neighboring state of Rio Grande do Norte. And another 5 or 6 years later, another mine was discovered, which is called Quintos. Quintos, also known as the Wild mine. I'm going to show you a few photos from the mines and a few photos also from stones recovered from these mines. And let's have a look what is so special about these stones. Now, in the Batalha mine, you find tourmaline crystals like these of various colors, predominantly blue, green, purple to violet crystal and crystal fragments, which are found in granitic pegmatites. The pegmatites actually consist of feldspars, mostly albite, quartz, and muscovite. This slide was provided by Brian Cook and shows sorted melee-sized untreated tourmalines from that mine. And because these tourmalines were so different from everything else that existed before, they were called Paraiba tourmalines in the trade to make them different from all the other tourmalines. Now, what is so special? These tourmalines, if we look at the absorption spectrum, are basically colored by the trace element copper. As you can see here, there are two copper bands. One is located here at around 750, and there's another one located here in the infrared at around with a maximum at around 950 nanometers. And there's also manganese 3+, leaving behind transmission maximum in the blue and in the green, resulting in a bluish green stone. And actually a turquoise colored bluish green stone. However, the first stones that we observed, that we had in our lab, they all showed this color. They actually were sort of a tanzanite blue. And these were unheated stones. This stone had a weight of, and all these stones we had in our laboratory, we certified them. This stone had a weight has a weight of about 5 carat. This is from Batalha. This stone had a weight of 12 carat from Batalha. And this is an exceptional stone, which is also from the Brazilian deposit of more than 60 carat, more than 65 carat actually. So these are unique specimens for Brazilian Paraiba tourmalines. Normally, Paraiba tourmalines from Brazil are less than 1 carat. Now, if we are looking at the chemical composition, we see elevated manganese concentrations and we see elevated copper concentrations, which were never been heard before in tourmaline of any color. Actually, the presence of copper already alone is unique to these Paraiba tourmalines. So those from Brazil, commonly colored blue, bluish green, green, and commonly, as I mentioned already, weight below 1 carat. And chemically, they belong to the Elbite tourmalines. Now, what is important is the difference between Cuprian and non-Cuprian tourmaline. They are very nice, beautiful non-Cuprian bluish tourmalines, like this specimen here from Namibia. And in some cases, it's really difficult to tell the difference. And also for those who are, and this is why I show this graph, who are also using or only have the opportunity to look at the stone with a handheld hand spectroscope. If you just look at the visible part of the electromagnetic spectrum, so the red is a copper tourmaline, and the green here, that's the iron colored tourmaline. You can see that if you look between 700 and 300 or 350 nanometers, there's not much big of a difference. So actually you cannot differ between the two with a handheld spectroscope. You have to use a spectrophotometer to actually detect basically here the second copper absorption band to tell that it is the Paraiba tourmaline. These are absorption spectra for green Paraiba tourmalines with, again, the 2 copper bands with iron titanium charge transfer and manganese titanium charge transfer, and leaving behind maximum in the green and in the blue area part of the visible spectrum. And on the right, there is a spectrum, a non-polarized spectrum of a purple copper-bearing tourmaline. Again, you see the 2 copper bands and you see a distinct absorption band of manganese 3+ with the absorption minimum in the blue-violet and in the red part of the spectrum, which produces the purple color. Now, what you can do with this type of stone is you can heat the stone to get rid of these manganese absorption band. So, and this is shown here, this is an unheated copper-bearing tourmaline of a purple color. This is the corresponding plot point in the color circle. And if you heat treat the stone, you actually reduce the manganese bands, both bands here, leaving behind a transmission maximum here in the blue to green part of the visible spectrum. So by heat treatment, you can produce this color from this color as a result of manganese, of reducing manganese. This is another example of heat treating with stone. We did that at the very beginning when we first had the stones in the lab from the Paraiba mine, starting with a dark blue color, heating it up here at a temperature of 600 degrees, resulting in a medium greenish blue. We just reduced the manganese 3+, and at even higher temperature, the stone turns lighter but also brighter. But there is still some manganese present, so the presence of a manganese band, of a small manganese absorption band, is not necessarily a proof that the stone has been, that the stone is unheated. So it's very difficult to identify of whether a Paraiba tourmaline is heated or not, and in many cases it is simply not possible. Now, these are photos from the Boron or Molungo mine that produces Cuprian tourmaline since 1991. And this is from the Quintos de Bajo mine, or the Wild mine, which is also known, which produces tourmaline since 1996. And both mines actually are not located in the state of Paraiba. They are located in the state of Rio Grande do Norte. Nevertheless, there are Cuprian tourmalines, some examples. Again, here, mostly the tourmalines, you hardly get very nice crystals. The tourmalines are commonly brittle, as you can see here, or as you can also see here, and it's virtually impossible to cut large stones out of these. But again, the production is slow. These slides here, these photos have been made some sort of 20 years ago or so. This was made relatively recently. Now, if you look at the genesis of the Paraiba tourmalines, as I mentioned, they are found in granitic pegmatites, which have been formed which have been formed some 650 to 500 million years ago. And these pegmatites belong to the so-called Brasiliano orogeny, which is a large-scale tectonic event. This actually is a result of the collision of West Gondwana, which is made up of South America and Africa, and East Gondwana, which is made up of India and Antarctica and Australia, during that time, so some 650 to 500 million years ago. And this Brasiliano orogeny has its continuation also in Africa. And in Africa, this is known as the Pan-African orogeny. And you can see one very famous gem-bearing area is the so-called Mozambique belt, which actually forms part of this Pan-African orogeny. And you also have this Pan-African orogeny in Western Africa, or Central Africa, Western Africa, sorry. And the state of Paraiba is located here. And when we now jump into Africa, we will land in Nigeria, which is located approximately here. And it was actually in about 2000 when the first Cuprian tourmalines from Nigeria appeared in the trade. And they were found at the mine near Ilorin, and the mine which is called the Ejuku mine, some 150 to 200 kilometers east of the border to Benin, and some 20 kilometers south of the village or the city Ilorin. Now, most of these stones that appeared in the trade were sort of violet to purple. They were rounded, they were rough, so they came from a secondary deposit. They were water-worn, not crystals like we saw them in Brazil. And this is quite a large stone of about 200 carats, if I remember correctly. And these stones were also heated, and then they produced, at the very beginning, most of the stones that appeared in the trade were sort of this type of aquamarine colored stones, but now you can also find very nice, bright turquoise blue, and particularly also green, bright green stones, but they also have colors like purple, light green, as I mentioned. This is a whole range of tourmalines, of Cuprian tourmalines from Nigeria, and this is a multicolored stone also from Nigeria. Some of the stones were larger, commonly above 5 carats, but again, very often a lighter type of aquamarine blue. But from Nigeria, we also know or are aware of very nice bright neon blue stones and also bright neon green stones. Also, the Nigerian specimens represent Elbite tourmalines with elevated manganese and copper concentrations. Most of the Cuprian tourmalines that we have today actually, however, are from Mozambique. And they have been found at around 2004, 2005 in a village near Mavuko, in the Nampula province. In Mozambique, also a secondary deposit, as you can see here. So these are not primary deposits. And Mavuko also produces quite some large stones. This is a processing plant, and you can see here that the stones actually, there's hand sorting. The stones are picked up by hand after they have been processed. And this is a very typical examples of copper manganese bearing tourmalines from Mozambique, from Mavuko. This is untreated material. Here you can see some very nice specimens between 10 and 20 carats. So Mozambique also produced larger sizes. This is an exceptional, almost 200 carat Cuprian tourmaline from Mozambique, designed by Tom Munsteiner. Again, purple stones can be heated, and as a result of the heat treatment, you get rid of manganese absorption, leaving behind a blue, greenish blue, bluish green stone. However, in many of these tourmalines coming from Mozambique, the concentration of copper is so low that when you heat treat the stones, they get almost colorless. Yeah, if you have a stone where the copper concentration is low, so that you virtually don't have any absorption here, so if you heat treat the stone, the absorption spectrum will look like this, so just a straight line here, and the stone then is almost colorless because all the light can go through, there is no selective absorption. So you have to be very careful, and you have actually to analyze the absorption spectrum first before you heat treat the stone, which we do for the trade. You can restore some of the color by irradiation, because by irradiation you can again oxidize the manganese, but then it results more in a purple, pale purple amethyst type color, which is not very attractive. Then there is an occurrence which is very close to the Mavuko occurrence, at the occurrence which is located at the village called Baraka. There you predominantly find this type of stones, and if you heat treat them, they produce this very nice turquoise blue Cuprian tourmalines. And what is interesting about those is that these stones, and only the turquoise blue stones, show a distinct luminescence, fluorescence, when you illuminate them with long-wave UV light. And the stones, both the unheated and the heated stones, however, showed a very strong photoluminescence when you illuminate them with a 785 nanometer laser. So this spectrum is taken with Raman spectroscopy, and you can see here these Raman bands, which is a result of rare earth concentrations, particularly neodymium. Now, we were interested in why both stones, unheated and heated, show rare earth luminescence, but did not show the luminescence under UV light. So what we did is we heated stones. So we took one, this is a sample that we just sliced into two pieces. The one on the left we kept as a reference, and this one we heated. 400 degrees, you see already that the color is changing. 450, the stone is already blue. 500 degrees, sort of a greenish blue. And then at 550 degrees centigrade, we stopped, being behind this very attractive colored stone. And now we look at the same under UV light. 400 degrees, and here you can already see that something is changing here. And at 500 degrees, this stone starts to fluoresce in this bluish color. And after 550 degrees, you can see here this luminescence, which is actually induced by heat, and probably also a result of balance change of manganese, but we're still working on that. Now, the interesting thing about these Cuprian tourmalines from Maraca is that they are not elbaite tourmalines. Like most other Cuprian tourmalines, they belong to the tourmaline mineralogical type. Now, we can chemically subdivide tourmalines into calcic group, vacant group, so where the X position is vacant, and alkali group tourmalines. And these Maraca tourmalines, they all plot here in the calcic group, where all others here plot in the alkali group, and they are all elbaites. And the one from Maraca, they are lidicotites. And they also have elevated lead concentrations. This is one possibility that may help you to separate tourmalines, Cuprian tourmalines from various occurrences. So this is lead-beryllium ratio versus gallium concentrations analyzed by laser ICP-MS. We see here that many Nigerian stones show high lead concentrations, actually high lead-beryllium ratios, and low gallium concentrations compared to the stones from Maraca that show high lead-beryllium ratios and high gallium concentrations. I'm not going to talk about in detail about the separation of the provenance of Cuprian tourmalines. This will need another talk. So to summarize that, the specimens from Brazil, Nigeria, Mozambique represent copper and manganese bearing varieties of tourmaline. The color is due to copper, and they are formed in a very similar geological environment. And this is important to remember. And there was some discussion going on at the nomenclature of Cuprian tourmalines. Should we only use the term Paraiba for specimens from Brazil? We think, and many others think, that we can use the term Paraiba tourmaline independent of the country of origin, because the term Paraiba tourmaline actually refers to a blue and green tourmaline which is colored by copper. And both the SIPSHO, this is just extraction from SIPSHO Blue Book, and also the Laboratory Manual Harmonization Committee agrees with that, so that you can use the term Paraiba tourmaline for Cuprian tourmalines. It doesn't matter where they come from. Now, the situation today is that the Brazilian specimens, the supply of Brazilian specimens is very low, commonly Milisenda and matrix stones. Nigeria never had a continuous production. Mozambique is producing an increasing amount of cabochon quality material, and this is why we increasingly see stones which are clarity enhanced, like the one that you can see here. There is a large fracture or fissure which is filled with some organic material. But not all of the foreign substances that you see in a fissure is clarity enhancement. Here, in these fissures, we can see, or we can identify that this is not clarity enhancement, so this was residue of the polishing powder, whereas this here is fissure filling. So there's commonly a tendency, not only for tourmalines, but also for other stones, that there's an increasing amount of parallel enhanced stones on the market. Tourmaline imitations, the most common tourmaline imitation actually is synthetic spinel and glass, green synthetic spinel and glass, green glass. But for Paraiba tourmalines, we identified, for example, these were all stones that we are submitted to the laboratory. In the center, this is a Paraiba tourmaline. On the left and on the right, these are apatites. And this is a Cuprian tourmaline, this is a Cuprian tourmaline, this is tsabolite garnet. And then also important is that there are a number of non-Cuprian tourmalines that look similar like Cuprian tourmalines, but they cannot be called Paraiba tourmaline because they have no copper, which is the case for these stones here. Composite stones, so doublets and triplets, are also used to imitate tourmaline. These are topaz doublets, and here you can see in the microscope this blue color in the cementing layer here and here. This is a quartz barrel composite used to imitate bicolored tourmaline. This is a synthetic corundum that we identified in the parcel of Cuprian tourmaline rough. And this is an assembly of Namibian minerals. So aquamarine actually and tourmaline cemented together in a matrix or in a mica schist looking like artificial something. Just to summarize, the various colors of tourmaline, as I mentioned, they can occur in every single color. In the trade, we commonly find in the names, the variety or trade names, Paraiba, indigolite for blue, chrome tourmaline for green colored by vanadium and chromium, verdolite for green, Canary tourmaline colored by manganese predominantly, rubellite colored by manganese predominantly, which retains the color also in incandescent light, and the completely colorless tourmaline, which is chemically almost clean, is called achromite. Achroma, no color. And these are the corresponding tourmaline species. Most gem quality tourmalines actually chemically are elbaite tourmalines. Coming back to the most important occurrences, and this is, I think, is also my last slide. So predominant tourmaline occurrences are in the United States, the Pará district of California. Then we have various deposits in Brazil. This is the famous Cruzeiro mine. Then here we have the deposits Paraiba, Rio Grande do Norte in northern Brazil. Then, of course, Minas Gerais, Espírito Santo in Brazil. Then Nigeria, Namibia, and then various other occurrences in Africa, Madagascar, for example, for the lidicotite, crosscuts, Mozambique for Cuprian tourmalines, and then other occurrences, Tanzania, Kenya, chrome tourmaline, and then Zambia, which is also an important tourmaline producing country, Congo, Rwanda, I forgot. These actually are tourmalines from a relatively recent deposit in Congo. Then Pakistan, Afghanistan. This is a nice specimen from Afghanistan. Then, of course, we have very nice tourmalines in the Ural Mountains in Russia, and there are also tourmalines in Myanmar and in Vietnam, or just to name also some of the Southeast Asian countries. And I think this is all my talk, and I say thank you for listening. Thank you for the invitation. And this is a very nice Baroque-shaped Paraiba tourmaline with a weight above 50 carats, designed by Ingo Hen and mounted in a brooch with diamonds. And this is a Paraiba cocktail. I thank you very much for listening. And now I go back to the screen.
Okay, thank you so much, Dr. Milisenda. It's really a wonderful webinar, and you will make it very clear for us to understand. Thanks a lot. Yeah.
I hope so. I hope so.
I like your speed, like very clear, and we can easily get your idea. So thank you so much for your patience, for being slow and be patient to explain everything to us.
Yeah, well, I'm just now looking.
Yes,
I'm looking at the various questions.
yes, you can take your time to review the questions. Now I launch the polling for you. Okay, yeah.
Okay.
So here is a small quiz to test how much you have learned from the webinar. So don't worry about it, it's just anonymous. So won't show your name there.
Okay. The question, one of the questions I can ask of whether there are any natural, not heated Canary tourmalines. Yes, there are. But if you have, if you're looking, like there are also natural colored Paraiba tourmalines, bright neon colored. Not all of the Paraiba tourmalines are heated. The problem is we cannot always tell. Now there's another question. Can you hear me?
Yeah, we can hear you. We can continue, yes.
There is another question, how indicolite is different to Paraiba tourmaline. Well, Paraiba tourmaline, the color is due to copper. Indicolite, the color is due to iron. So there is a significant difference. And of course, and because of that, there's also a huge difference in price as well. And therefore, it is important that you are able to identify of whether a tourmaline is colored by copper or not. If it is colored by copper, you can find them, you can call them Paraiba tourmaline. Then there is something which I try to point out. There is a question which it is important for me to remember that the Paraiba tourmaline. Oh, it's a question from Adolfo. Hi, Adolfo. Paraiba tourmalines can be obtained not only from different states in Brazil, then Paraiba, but in other places in the world. Can we use commercially the name Paraiba elsewhere? Yes, my answer is definitely yes. Now, there have been arguments that the term Paraiba should only be restricted to Paraiba tourmalines that come from Paraiba. Or actually, first of all, they said that only from Brazil. So this means that all the others from Rio Grande do Norte cannot be called Paraiba. So only those stones which come from Paraiba should be called Paraiba tourmalines. I do not agree. In the state of Paraiba, you also have tourmalines, for example, which are black. Should we call them Paraiba just because they come from Paraiba? No. In my opinion, a Paraiba tourmaline is a tourmaline that is colored by copper and manganese. Of course, they have been first found in the state of Paraiba, but they are also found in other places in the world. So the term Paraiba, or if you wish, Paraiba type tourmaline, can also be used for other stones from other occurrences.
Okay, so Dr. Milisenda, maybe we can go back to the polling first. So
yes.
I will end the poll and I will share the results. So you can explain to them one by one. Yes, thank you.
Yeah, so let's start with the term. First question, the term tourmaline refers to a single mineral. Well, 2/3 had that correct, more than 2/3, 76% has this correct. They answered false. No, the term tourmaline does not refer to a single mineral, it refers to a mineral group. Pleochroism plays an important role in tourmaline cutting. Yes, of course it does. Think about the various shapes of green and red tourmaline. It's depending on the pleochroism of the stone. Canary tourmaline is a trade term for yellow tourmaline enriched in manganese. True. Also 73% had that correct. Paraiba tourmaline is colored by iron. 92% had the correct answer, that it falls. And that's the most important thing about Paraiba. It's colored by copper. Tourmaline can be enhanced by heat. 101% true, 2% false. How you come that you have more, that you have above 100%? I don't know, but okay, everybody, most of you had that right. So you have at least you have learned something about tourmaline. I'm very happy for these answers.
Okay, so we finished already, right?
We finished with the polling, yes.
Yes, so I will give me 1 minute because I saw some attendees, they are leaving. So I would like to announce our next webinar on next Thursday also. It's about the, can you see my screen? It's like the poster about gem pegmatites. So we will invite Peter Lickberg, and he will come to give a presentation about the gem pegmatites. And he's a mineral collector, so he will try to display a lot of minerals, and he will try to explain how these gemstones are growing the pegmatites. So I hope you will come to attend next time. So I will give back this to Dr. Milisenda. So I will stop share. You can continue with the questions.
Oh, I can. Okay. Is the incredibly high price of Paraiba tourmaline justified? That's a good question, which I cannot answer. But you know, price depends on the demand. And the demand is high, the supply is very low, particularly for very high quality material. And I mean, when I remember correctly, there was the highest price for tourmaline was almost $200,000 per carat on an auction by Sotheby's in some 2 years or so ago. And when these stones first appeared in Idar in the end of the 1980s, there were at around $500 the carat, and which at that time was an extremely high price for tourmaline. But since then, you know, prices went up like unbelievable. So it's the demand that makes the price. Can Paraibas be identified from their RIs, especially with regards to other tourmalines? No, they cannot. They show the same refractive indices like since they are elbaites or lidicotites, they show the same refractive indices than other non-Cuprian elbaites or lidicotites. What kind of heat atmosphere is commonly used for Paraiba tourmaline? Oxidation or reduction? Oxidation. Yeah. Can we use the UV vis for country of origin? Tai-san, okay, hi Tai. Well, actually, no. I mean, well, let's say it that way. There are some Cuprian tourmalines from Brazil where the copper concentration is so high that you have actually complete absorption from 700, let's say from about 700 nanometers on towards the infrared. This is very rarely observed in Cuprian tourmalines from the other deposits. So if you see this, then it is not a proof, but it's an indication that the stone is from Brazil. Then there is another question. Do you call, this is also something I think is important to mention. Do you call Paraiba tourmaline some purple Cuprian tourmalines from Mozambique? Or do you note in comments that there are some copper inside? We do not call them Paraiba tourmalines. We only use the term Paraiba tourmalines for those stones which are blue and green, or where the predominant color is blue or green. The reason why we do not call the purple copper-bearing tourmalines Paraiba tourmalines is because there are some purple, no, not some, there are many purple and violet tourmalines where the copper concentration is so low that when you heat treat a stone, they get colorless. And so the term Paraiba tourmaline might imply that the stone is suitable for heat treatments, and we don't want to do that. And therefore, we only mention that for violet or purplish stones, that it is a Cuprian tourmaline. So we mention that there is copper inside, yes, but we do not call them Paraiba tourmaline.
So, Dr. Milisenda,
Yeah.
Dr. Ponsua has a question.
Yeah.
She asked maybe you can mention more about the Maxisi tourmaline. Maxisi 1, 2.
Is it in the chat?
Yeah, it's in the chat. Yeah, Maxisi. Yeah.
But Maxisha is not tourmaline. Maxisha is beryl.
Yeah, that's true. So I don't understand. Yes, I saw this question.
Yeah, but yeah, Poms is she retired.
Yeah.
Hi, Poms. No, Maxisha is about, that's a special type of beryl. Yeah. Yeah.
I have a question actually, and so I want to know how is the progress for the Paraiba tourmaline origin determination. So because I like now, people, some labs they judge according to the color, right, and also the chemical composition. So the chemical composition there are like sometimes is cross, right? So how do your lab judge about the origin for Paraiba?
Well, I mean, we do it basically also on laser ICP-MS analysis, but I must say that there are cases. So you might have particularly problems with stones coming from Rio Grande do Norte. The Batalha material is actually quite not, I wouldn't say easy, but let's say straightforward to identify. Material which is from Batalha mine, but there are some stones from Rio Grande do Norte where the concentrations like copper, gallium, lead, and beryllium, and all these elements that we use to tell the difference, there might be some overlap. Yeah.
Yes.
Yes, there might be some overlap, and then it's fair to say that you cannot determine the origin. Yeah.
So still maybe in the research progress, right? Maybe in the future there are some ways can be find out to see the origin determination.
Yeah, well, the research is still going on. I mean, we have we are still trying to get more and more stones of definite locality. That's always the most important thing. And the thing is that, for example, the Rio Grande material from Rio Grande do Norte has been mixed with the Batalha material. And so at the very beginning, it was not quite sure of whether, for the reference samples, of whether they are from Batalha or from Rio Grande do Norte, from Paraiba or from Rio Grande do Norte. So you have to make sure that you are looking at the material and you know where it comes from.
Yeah, that's true. Yeah. We have to know which mine it comes from.
Yeah.
Yeah, one more question. Because before I read an article about the copper diffusion in Paraiba, in the tourmaline.
Yeah.
So
I've never seen that.
Yeah, because I read an article about that. So I'm really curious about progress. Yeah.
Yeah. No. There's no copper diffusion, no artificial copper diffusion in tourmaline.
Mm.
Yeah.
There's an article I saw before. Yes.
Yes, but that's I doubt.
You doubt, right?
Yeah. I doubt that there is copper diffusion in tourmaline. I mean, you probably need a quite high temperature to induce copper into tourmaline, and I don't know whether the tourmaline will survive that.
Yeah, that's true. Yeah, because they always have like fractures, like these kind of things. Yeah.
There's another question here, which how is manganese 3+ reduced in oxidizing atmosphere? That's a good question. Because in oxidizing atmosphere, you commonly not reduce things, you oxidize things, elements. But there's always one element that oxidizes, and there's another one that reduces. Now, in this case, in heating and oxidizing atmosphere, I mean, that's a lot of theory behind it, but there is titanium is present in the structure as well. And the titanium will oxidize before the manganese will oxidize. So why manganese is reducing during that process, titanium is oxidizing. You see, if you have if electrons move, there are donators and there are acceptors. So in that case, there is charge transfer between manganese and titanium. And so the manganese is reduced and the titanium is oxidized. Are the effect of heat treatments and irradiation permanent in tourmaline? Under normal bearing conditions, I would say yes, the heat treatment is relatively permanent. Irradiation can be reversed by heat. So, I mean, irradiation oxidizes manganese. So you produce manganese 3+ from 2+, and heat treatment reduces it again. So under normal wearing conditions, I would say stable, but nevertheless at higher temperatures, you can reduce, you can actually lighten a pink stone that owes its color to irradiation. I don't know whether we still have time.
Yeah, so I think maybe this is almost of the questions already. Yeah.
I mean, please talk a little bit. Please talk a little bit about aquamarine versus tourmaline. I mean, they can occur together in granulated pegmatites, and they occur also. Aquamarines also occur in these Precambrian pegmatites. In these, for example, in Africa, in these Pan-African pegmatites. But this is a completely different story, and would need another hour to talk about.
Okay, so maybe one more question, so we will finish today's webinar.
Since chromium is rarer than copper, which is the coloring age of Paraiba, do you think chrome tourmaline is underappreciated? I agree. I mean, the chromium tourmaline is a little bit underappreciated, but the color of Paraiba, that is so exceptional. I mean, you find you find that the color that you find in chrome tourmaline, you find if somebody wants to have a chromium green and they're buying an emerald and want to spend a lot of money, they're buying an emerald. But there is nothing comparable to the turquoise color of Paraiba colored by copper. So that's why the Paraiba is so much more expensive than the chromium tourmaline.
Okay, so thank you, Dr. Milisenda, for your patience for answering all these questions.
You're welcome.
Yeah, we are going to finish tonight because it's the time already passed over 25 minutes.
So those people who have questions, they can just send me the questions to my email. Okay, so tomorrow we will have the follow-up email, and I will put your email address there. So they have any questions, they can send you email. Okay, good. Okay. Then I thank you all for listening and for these interesting questions. And thank you again, AIGS, for inviting me. Okay, thank you, Dr. Milisenda. And thanks all for your attending. And so see you next time. Okay, see you next Thursday. Bye-bye. Okay, bye-bye to everybody. Bye-bye, everyone. Yeah.